And then.
No problem. All right, let's talk about. We're going to review some free radical reactions, and then we're going to start talking about synthesis. So today, this is sort of review because synthesis is not any new reactions. It's how do we put together the reactions we already know in a way to make certain products. Okay. So this is a good unit to finish up with right before the test. So let's start with this. If you chlorinate each of these once, remember chlorination is our one where we can get all possible products. How many possible products for each of these molecules? If we're going to pull a hydrogen off and chlorinate each of them once.
You just don't like that number.
I mean, I would draw them too, but I suppose technically.
Okay. And the first one is going to be symmetrical. So really you can look different. Right?
Correct.
Yeah. But so this one isn't going to be symmetrical compared to not making it symmetrical.
So I get a total of 6, including stereoisomers. They're separate molecules. So which ones have an R and an S? That spot doesn't have an R and an S because you got 2 hydrogens that are symmetrical, right? That doesn't have an R and an S because both directions around the ring would be symmetrical. These 2 positions, though, each are going to have an R and an S. But and actually, if we were actually, I think there's more stereoisomers because this position is a stereoisomer also for each of the positions here. So these first two, one molecule, one molecule. I'm gonna erase those so that we can see the other ones here. Because if we can put, if this one, let's just decide that the methyl is sticking up towards us. There's no stereochemistry, so we can just take which direction up to this. But that means each position here, we could have the cis and the trans. And the cis is gonna have an R plus an S.
So really we should be saying R plus S and cis plus trans.
We have to be careful because we're gonna over-represent that way. The other way that you could think about it is you can have cis plus trans here. But that's not the same molecule as cis plus trans here.
Right.
Because we get the R versus the S in each case. So that means two stereoisomers here, two stereoisomers there, and then same for each of these. There's this one that could be cis or trans, and this one that can be cis or trans. So there's a total of 4 stereoisomers where you put on one of these 2 carbons, 4 stereoisomers here, plus the one there, plus the one there. So 4, 8, 10 total if we count all the stereoisomers.
Cis and trans or RNS? Different things.
You can do it either way. If you're going to use R and S,
We have to draw the.
You have- yeah, I think that the easiest way to show all the possibilities is to do it like this. Because if we're going to actually show all of them, here, let me white out the screen real quick so I have lots of room. All right, so let's just look at these 4 first. These are going to be separate stereoisomers because for this one, they're all going to be, let's say, 1 chloro, 2 methyl. Cyclopentane. So for this one, carbon 1 is always going to work the chloride for these. So carbon 1 is going to be 1, 2, 3, and 4 is already at the board, right? So that's going to be 1 S. And then the other stereos is right here, and that one's going to have the priority is going to go 1, 2, 3, and the hydrogen is the other one. So that's going to be R, 2R. The other one that is cis is this version, right? So if cis and trans is all we need to think about, then we should get the same stereochemistry on both of them.
Yeah.
Here we're gonna have 1, 2, 3 hydrogen into the board. So that's 1R. And here we're gonna have priority is gonna be 1, 2, 3, 4 is into the board, which is S. They're both cis, but they're enantiomers of each other. These ones are both trans, but they're enantiomers of each other. So that means we get, and if we actually look at, we count this one, 1, 2, 3, but the hydrogen's coming towards us. So that would look like 1, that would be S, but we're flipping it to 1R. And this one's going to be 1, 2, 3. So we're going to get all 4 possibilities for each of these. So that's the other way that you can think about it, is because this gives us 2 stereocenters. So this is carbon 2 with the methyl line, right? So if this is our priority 1 to 2 to 3 for this is carbon 2. So basically for this one, we're going to get, and then what would we expect this one to be? We can figure out what the other combination is.
2 R 1.
We already have that one.
Yeah.
We have 1s2r, 1r2s. We have 1r2r.
2 R 1. Or S.
Carbon 1 can be R or S. Carbon 2 can be R or S, which means there's 4 possible combinations. That same logic holds up when we put the chlorine in this position as well.
Yeah.
So there's a total of 8 isomers, 8 products without even getting to these last 2 spots. Here and here. So the position that didn't have any stereoisomers, we're putting it on. So it would be 1-chloro-1 methyl. Or we could put the chlorine on the methyl group itself. Those don't have any stereoisomers. So one of the things that almost makes this a little bit easier is that because it's monochlorination, we're going to get everything. So as soon as you can recognize that you're making 2 stereocenters is going to have 4 isomers just for that constitutional isomer. Right? And remember, you can think of it, you think of R as flipping a coin heads up, and S is flipping a coin that comes tails. And this is flipping 2 quarters. There's 4 possible outcomes. Tails, heads. Heads, heads. Heads, tails. Tails, tails. Just like your Punnett square we were talking about the other day, Felix. We think about Punnett squares for genetics more than anything, but they're actually really useful anytime you've got a set of like binomial options. You can make something similar. It's just when you start getting, if we had 3 variables, it wouldn't be a Punnett square, we need a Punnett cube.
Right.
Because you need a Punnett square in 3 dimensions. So when you start getting past 2 variables, it gets harder to visualize.
Yeah.
But it's still just counting possibilities, right? It still always comes back to that. All right. Questions on this one? Should we do another one?
Yeah.
I don't know if there's any that are as tricky as that one. That might have been the trickiest one.
That was cute. We say that where's the respect. Okay. Yeah. But I think my house is for A, is they gonna be flat or you can get like out of the border?
For A, you get the point coming out of the border into the border, but that's there's the same stereo because both directions run the rings. So you were right, only one product for A. 10 for B. 1 for F as well, same logic, yeah.
She is gonna be the same as B.
G is gonna be the same as B. Almost. We have 1 extra carbon, so I think we get 1 extra, I think we'll get a total of 11 in this case. C is simpler though. Because you only get 1 stereo center for each of these, because you have 2 identical metals here. So there is no sister trains for that. So you can put 1, 2, 3. Those are both still going to be stereo centers once we chlorinate. But they're going to be the same as the ones on this side. So we're going to get a total of 1, 2, 3, 4, 5. Only 5 for C. Because we can't add a chlorine here. Because it already has 4 bonds.
Right. So now that it's top, she's really the risk of house. Well, it can go in, but it's not going to be citrus with standards with we can get sure of lots. There's as one was the nestle. Yeah. Or whatever the circuit.
These are our 5. C. Sometimes trying to do too much in too small a space can get in the way because you wind up confusing yourself. So sometimes it's worth taking the time to write them all out, even when they're just different stereo instruments, because then we can see we don't need to do one on this carbon, because if we did put one on that carbon, let's see, I put that one sticking out, it's the same as this. Because if I took this and flipped it like a pancake, we get the same one.
So, and everything is so very. It's a good thing.
All right, what's next?
We're getting hard.
For D, I get 5 as well.
They can't go on the top of the map. So that would be the same.
Bingo. Only one of the positions in this case has a stereo isomer.
Okay.
So that kind of simplifies things. H is another simple one.
Oh, there's.
It's very symmetrical. These carbons don't have any hydrogens. You could put chlorine on. And all of the methyls are symmetrical to each other. So you only get one option for H. Despite looking like a complicated molecule.
Right.
So we could put a chlorine here. I can't put a chlorine there, I can't put a chlorine there. Do the same thing, because all of these metals are identical to each other.
And there's just.
There's no stereochemistry because there's 2 symmetrical hydrogens left on each of these, right? So there's no R plus S because you get 2 identical hydrogens on each of the metals. You could chlorinate. So just one product there. The other way to think about it is think about it in terms of NMR. If we looked at proton NMR for this one, all of the hydrogens are identical, so we should only see one peak, right? Which means there's only one product, chlorination. All of these metals are identical as well, right? So we can put it on carbon 1, and that covers all of these others as well. And there's no stereochemistry. But we could put it right here. And that one's gonna have an R plus. Should we do the other tricky one? Let's finish with G.
So, if I do about citizen trends in relations to the network, are they then also on plus? Because like this one,
So cis,
right, but if we were to flip it, then it would give me the one that's over here, right?
right,
So I should say that it's also. If I'm drawing it,
you have to find a way to draw all four of them.
yeah,
And the easiest way to do that is, is to either draw, so cis here, you could draw cis here and keep that in the same spot, right?
yeah.
That's gonna be two of these options. Then you could do trans here and trans here. That's gonna be the other two options. So if you're gonna think about it in terms of cis and trans, you have to think about it in terms of both of these carbons. If you're just gonna look at it in terms of R versus S, this covers the cis trans isomers. So I haven't even counted those yet. We have 8 just looking at these two positions. Here and here.
These. Yeah. Oh, I just tried it, yes.
So we have that, right? We can do the same thing with the chlorine, chlorine up and chlorine down, but with both of the methyls down. Chlorine up, methyl down. Let's look at it. So this one's cis. And the stereochemistry for this position is going to be 1, 2, 3. So it's going to be 1R. And then this position, stereochemistry is going to go 1, 2, 3. 1, 2, 3. So that's going to be 2S. Right? This one's not quite the same. Because it looks like they're still both cis, but we flipped both stereotypes. So this one's going to be 1S, 2R. And then our trans ones have the same issue. This one's trans, but it's not the same molecule as the other trans one because they're opposite directions. They're enantiomers to each other. The 1R2S is the enantiomer of 1S2R. They're both going to be cis, but they're reflections of each other. And then 1R2R is the enantiomer of 1S2S because we flipped both stereos. So quick review. What's the term for stereoisomers that are not enantiomers to each other? So we flip one of the stereocenters but not the other.
And let's make it the cis group.
Right, but that's, so it's going from the cis to the trans. They're not enantiomers because we flipped one stereocenter but kept the other the same.
Yeah.
Enantiomers, you have to flip both of the stereocenters. We had a term for this. We flip one but not the other. Over the diastereomer. Remember that? There you go. You don't remember going back to the midterm last quarter where we said it was multiple choice basically, right? I gave you two molecules. I said, are the top two molecules the same molecule, enantiomers, diastereomers, or constitutional isomers? And the constitutional isomers would be like these two. Same formula, but we actually put chlorine on a different carbon. These two are going to be diastereomers. These two or these two are going to be enantiomers. All right, so we've got 8 so far, and we haven't touched the last spot, last 2 positions. 3. Sorry. Sorry, that's the same one.
Yeah.
So now we're up to 10. We can also do here. So for these ones, if we flip this methyl group so that it's down, that's the same as this one because we can. That's the same thing we started with. So these ones are cis and trans, but they don't have R plus S.
I don't know.
Because both directions around the ring are the same. So I think that gives us a total of 12 for them.
So that,
And if we were trying to separate these out ourselves, if we did this reaction and then we were trying to separate these out, we'd probably wind up separating them out in like stages because these ones, all 4 of these are going to have really similar properties that might not be the same as these or these. So we basically get all the stereoisomers together and then separate those out from each other. And there's a couple of ways we can do that.
the same plus E is the same.
Yes. But we would never say R plus S if there's 2 stereocenters because we need to be careful which one we're talking about.
Erase this one part. And the stereo center and the carbon are also the same.
Chirocarbon is a stereo center, not to be a chirocarbon.
Oh, because they're not the.
It doesn't have to be carbon, and it doesn't necessarily have to be chiral. Think about our alkenes. Neither of those is a chiral carbon, but the alkene bond is a stereo center because there's two options for it. So it's same with these two. This whole ring, we call this entire ring is a stereo center because they can be cis or they can be trans, but it's not a chiral carbon. Chiral carbon very specifically means four unique things attached. So you get that non-superimposable mirror image. These ones, the mirror image is still superimposable. So it's not chiral, but it is a stereo center. All right. Well, that was a good warm up, right? Do you want to take our break now and then we'll do synthesis when we come back?
Okay, you want to.
45. 10:45.
Here's the pee.
Let's take a break now then.
Let's take a break. I want.
Come back at 5:02.
Come back then.
5:00.
Okay. You go upstairs for coffee. Just hug and have it out.
Really?
Yeah, I turned on for like 2 seconds.
Little sisters.
He was saying. And we really just want to just grab that stuff. Oh, I sure, here's some for you. Yeah, I was first searching in this book. So. I don't think I didn't even know about it. Not have space for it. Charge this, it's not. Charge this. It's very expensive, but I was trying to think. It's only that for modality. There's the wax. Dehydrated chicken meat for one. I just, I don't want to see, I feel like. Yeah.
Fruit damage can still be good if you're willing to, if it's nice enough that it's worth putting a little bit of effort into.
That's a fine. But there's like, I probably six, that's. Okay, where is this? Ah. It's in Susanville. Taylor, do you know how, that's, we have to do that 2.5 weeks.
It's 2.25 hours away, maybe 2.5.
That's too far to be hauling stuff. Good night. I'll sit in the back. I won't bring my.
All right,
He wants a bread maker.
a bread maker.
There's some cheap ones on my photo. I was looking at some used ones. Yeah, it's the flowers, the one and press one, and it comes from fresh bread. It makes everything, that's everything. Oh, you want. I think I want things and grace.
Thing is, you'd probably be better off just making your own bread, because when you get good at it, it doesn't take very long.
But I'm busy.
It's true.
I just started in the morning. Easy peasy, Sean.
It's true. All right, let's talk about synthesis.
Okay.
So synthesis is not anything new, it's just a different way of looking at the reactions we already have. So Taylor, you might not like this because it might force you to reorganize your reactions in your table. But on the other hand, it's gonna make it a little bit, it's gonna give you a different way of looking at things, which should give you a better overall view of things. You know, when you're driving around, you have one sort of mental picture of how the town is lined up, right, based around roads. If you're walking, you need a totally different viewpoint, right? I'm not gonna go out and around, I'm gonna walk through the meadow because there's a bike path there, right? So having different ways of viewing this, different sort of layers of thinking about things can be really helpful to help make some of the other things make sense. So for starters, we're going to approach these reactions in two different categories. They're either functional group transformations, meaning start with one functional group, make a different functional group. So that includes everything like substitution. It can mean hydration. It can mean turning an alkene into something else, turning an alkyne into something else. But all of those different functional group transformations are just one way of sort of arranging where things are on the carbons you already have. Right, and so we can kind of break those down into a couple of categories too. We can move where a halogen is. And halogens are really handy because if you can move where a halogen is, a halogen's a really good target for a substitution reaction, right? So you can always replace a halogen with something else if you can put the halogen in the right spot. So if we want to move a halogen, usually what we do is we do an elimination reaction and then we do an addition reaction. And because we can control with our choice of base, we can control whether we get the Zaitsev or the Hoffman product. And then with our choice of addition reaction, we can choose whether we get Markovnikov or anti. That allows us to sort of move things around the molecule pretty well. So that's going to be one of our primary tools. And we can do the same thing with pi bond. We start with pi bond, we can do an addition and then an elimination. we can kind of pair these together and we can go multiple steps to put the halogen anywhere we want. Then the other option that we have is if we have a double bond or triple bond, we can convert back and forth between them. So we can do partial hydrogenation of a triple bond to get a double bond. We can hydrogenate a double bond to get a single bond. We can do an elimination to get to a double, and then another elimination to get to triple. So we can go back and forth in all of these different sort of variables, all these different axes. Right, so if we're moving anyway, here's a zoomed in version of what we were just talking about. Let's say we wanted to put the bromine here. We started from this molecule, but we don't want the bromine there, we want it on the tertiary carbon. We do an elimination, and then we can do an addition. This elimination, we would want to be often, or sorry, we want it to be the Zaitsev.
Which means what?
Which means we're gonna make them more substituted alkene. And then for our addition, we want it to be Markovnikov. So we want to put the bromine on the most substituted carbon. If we wanted to start here and go the other direction, if we were starting here and we wanted to put the bromine on carbon 1 instead, we would do Hoffman. Because then we would get this elimination. And then we would do the anti-mark. To put the bromine there. So starting from bromine anywhere on a molecule oftentimes is enough for us to then do this in the right order, say it's then Markovnikov or Hoffman followed by anti-Markovnikov, to put the bromine wherever we want on a molecule. Right, but those are the two variables that you think about. When you're doing an elimination, you think about Zaitsev versus Hoffman. When you're doing addition, you think about Markovnikov versus anti. All right, so here's one way to think about these reactions. This is the same information that we just kind of drew, just with all the details filled in. If we're starting here and we want to make the Zaitsev product, we use a strong base, but not a sterically hindered one. Once we get here, if we want to do the anti-Markovnikov, we do HBr with Rohr. HBr with a
First one. Do we say it's that or how?
So this would give us the Zaitsev product because it's not sterically.
This TVOK is also a strong base, but it's not ster, or, but it is ster.
Correct.
that's the TB. That's the strongest there.
Correct.
Is it?
The other one that you see is DBN, which is dibutylamine.
Okay.
But this, we usually use this one.
And for the anti-harm, that's the. Is it the HBr and the word?
Yeah.
Yeah.
Correct.
Okay.
Is anti-Markov prohibition, so it's gonna take this pi bond and break it.
Does the spirit be inserted in base?
Not for addition reactions. The sterically hindered base matters for the elimination reactions. We're just gonna take the product of an elimination reaction and then follow it up with addition.
And safe test always needs a strong, non-hindered. base.
Correct. So either hydroxide or ethoxide are both common cases. The reason ethoxide gets used a little bit more often than hydroxide is because hydroxide is also a strong nucleophile. And this is a little bit less strong of a nucleophile.
Because with the hydroxide, we should end up with alcohol, right?
So basically, we can start with the bromine anywhere we want and move it anywhere else on the molecule by doing these in the right order. Right? If we started with the bromine all the way over here and we wanted to get it to that side, it might take us a couple cycles of this, but we could do that. Which then opens us up for, now we can replace the bromine with whatever other nucleophile we want. If we put it into substitution conditions. If we wanted to move an alcohol instead, it gets a little trickier. It's a lot easier to move the halogens because they're already such good leading groups. But we can do the same thing with alcohols. We just need to turn the alcohol into a good leading group before we can do the elimination reaction. So do you remember this step, the O-tosylate?
Wow.
Basically, it is we write it like this, but basically tosyl chloride is, let's say it's S. That's the chloride version. And when you expose that to an alcohol, you basically pull the chlorine off and you attach the sulfur to it. And what that does, so we wind up with this, the O-tosylate is going to look like this, attached to whatever your R group is. But what this all does is it just makes it a good leading group. So then if you follow it up with a strong base, you can get an elimination reaction out. You just have to treat it first before we can just throw the strong base in there to convert it to a better leading group. So it's still the same thing. It's still an elimination reaction, and it's still going to be either Zaitsev or Hoffman. We just have this first step.
Because this is what? This is making a major good. No, something that you, it's yes,
Is TS. So this TSCl.
is the parentheses part without CL.
Right. Exactly. So
this is TS, and if the CL was for that left, it would be.
So this is. This part, after you expose it to TSCL. Which we always just gonna write that way, we're not gonna show the whole structure.
Which is the first thing you do.
Right,
We then have OTs.
which is this whole thing. We just almost never draw the whole structure out because we generally. Don't care about it. The whole point of the TS is just to turn the oxygen better leaving group. It did have some, I wanna say. It was used in. Late 1800s in medicine as some sort of treatment. That might be how it got its name.
So it's really,
But-
we can go back and we, yes,
Correct.
what we have been used for is.
It might be a false cognate. Meaning one of those things that looks like it has the same root, but it's not really the same.
Like the. Prenatal, little bit in that there's.
Right.
The pill that I don't remember taking for nausea, but they didn't know that the flips.
The Tosel group. You know what? Actually, I think it comes from it's toluene sulfonyl is the full group, is the full name. So it's actually not what I thought. The root TUS, like a tussin, is something that makes you cough. TUS means coughing. But TOS, which is short for toluene with sulfur on it. So they, cough medicine is an antitussive,
Right.
but
So then on the next slide, where did you say the state is that? For the alcohol
let's,
or the last one?
so both of these have the same first step, which is the tosyl chloride and pyridine. The pyridine is just there as the aprotic solvent. But then the second step is the elimination reaction. And it can either go zeta or alpha. Once we get to here, once we get to an alkene, we have Markov-Nikolov and anti-Markov-Nikolov hydration reactions, right? So we wanted to put the oxygen back on, but in a different spot. We would just, once we get to the alkene, we just do a hydration reaction.
Okay.
Right, so same basic logic as the slide before, just different reactants because hydration reactions were repetitive reactions than HBr addition. If we want to move a pi bond instead of moving one of these other functional groups, we just switch the order, right? You can think about how if you wanted to move a pi bond from here to here, we could do that. We have all the steps already drawn, right? Because we're just picking a different start and end. So it's a little bit, I've seen good overviews drawn like a subway map. Where you pick where you start, you pick where you end, and you take your route to get there. And sometimes there's more than one route, but either way, like it doesn't matter. We don't have to start here and end here. we can start there and end there just as well. It's still a matter of get from here to here, and then from here to here. So we just are switching the order. Instead of it being elimination followed by addition, it's gonna be addition followed by elimination. And usually if we aren't specifically trying to end with an OH group, we're gonna do all of our intermediates for the most part are usually gonna use a bromide. Because we know good high yield processes that give us an easy way to move bromine around that are easier than moving an oxygen around. And bromine's a better leaving group than chlorine anyway, it's easier to work. So bromines wind up being our default when we need to move something around. All right, so we have a similar sort of map that starts at an alkene and ends at alkene. Start with the addition or the anti-Markovnikov or the anti-Markovnikov addition, followed up with elimination.
Is synthesis going to be on the picture?
There will be at least one synthesis question. But it'll be a relatively easy one. The final thing what's different about that is I don't give any guidance and say, here's your stock room, make this molecule.
Right.
This one will be, here's your starting material, and it'll be at most like 2 or 3 steps on the midterm. And you don't have to worry about the practical side of it as much.
So this is very. You're just ready.
And it's the same variables. Markov versus the anti, or theta versus Hoffman. If we control those two things, we control where we're putting our functional groups. Last one. This one's a really easy subway. Because it's if you have pi bonds and you want fewer pi bonds. Or if you don't have pi bonds, but you would like pi bonds.
Right.
So these are still going to be a lot of times addition followed by elimination. But we have a way to go from an alkyne to an alkene to an alkane, or we can go from an alkane and get to an alkene. Because we can brominate. Now that we have free radical reactions, we have a really easy way to take something that's just carbons and hydrogens with no functional group, and it gives us a functional group when we brominate. So because all of our other steps, those last few pages, were reliant on we have to have a functional group in order to do something, right? So bromination and free radical reactions in general, it's going to be the way to start from something simple like ethane and turn it into something we can do reactions with. And so if you're starting with an alkane, the very first thing you're going to do almost always in the synthesis problem is throw a bromine on it. And that's not just me saying that. I pulled this out from the Klein textbook. If your starting material is an alkane, the only useful reaction you should consider is radical halogenation. There is no other place to start. The only other reaction we know for an alkane is the burning, which doesn't help with synthesis. Let's do practice. we're trying to get from this molecule to this one.
And then attach, well, I'm just knocking out my number of them. And then attach the room to the next substituted. That makes sense?
Yeah, so you can use similar logic and similar approach to this as doing your mechanisms, where you memorize like landmarks along the way. You don't need to know every detail, but you can be pretty sure, like, well, if I'm trying to put my bromine all the way at the end, I know I'm gonna have to start from a high bond rate. So that gives you a landmark. And so they call that process retrosynthesis, where you work backwards.
Right.
So if I know I'm trying to get to here, then that has to come from here.
So we do HBR at first, to get our energy. And then add TU, that's to move the bond.
Well, so we can fill in this section first.
Oh.
This is gonna be definitely to go from here to here, is gonna take an HBR.
Right.
And a Ruhr. Because we need to do the anti-Markov competition, right? So how do we get from here to here? That's our moving pylon, like you suggested. So we're trying to put a pylon at the end. We need to get here. And you can fill in the individual reactants as you go, or wait until you have your plan. As long as you know that this is a step that we can do.
Right.
We don't need to fill these in, but while we're thinking about it.
Yeah.
our starting material for this one. Yep. Yep. If we want to keep moving the functional group in the same direction, we're gonna wind up using the same reaction more than once. Because we do an anti-Markov competition followed by Hoffman elimination, followed by another anti-Markov competition.
How much do people do this all day get paid?
Synthetic chemistry?
Yeah.
It can be a lot if you're doing it in private industry. Because a lot of, well, the window on that may have closed a little bit because pharmaceuticals are moving in different directions. But basically, if you can reliably make molecules that other people find industrial uses for, whether that's pharmaceuticals or something else, then it can be a really big deal. Pharmaceuticals, oil industry, things like that. That's a really huge industry. And it's working in something like, just because I know the numbers in chemical engineering, if you're working for Chevron at one of their refineries,
Yeah.
if you can increase the efficiency of refining by 0.1%, that can mean $1 billion for the company.
Right.
In a year, which makes you very valuable.
Yeah.
You can make your career on making one small change at a refinery that gets you a percent or two of extra efficiency. And so the same is true here. So a lot of times now it's more of an engineering process than it is actual science sometimes, because you'd be like, okay, we have a way to make this molecule, but it only gives us like a 10% yield. If you can get another 5% yield out of it by switching up what your synthetic pathway is, then that can be really, really a lot of money.
Right.
So in general, chemical engineer, that is more on the engineering side. If you're trying to find out, if you're picking the most biggest payout, chemical engineering is the way to go. Because people who do stuff like this for chemical engineering firms can earn, $250,000 a year by the time you're in your 40s. You don't actually start producing until you're in your 40s, which is funny. Because a lot of other fields, they want you as young as possible because that's when you have more energy, ideas, things. But if you go into synthetic chemistry for research, all researchers make about the same unless you happen to make a startup along the way. Which is actually a pretty common thing. While you're in grad school, if you see like, hey, this research I'm working on has this practical application, it's pretty common to then take your research, get your publish it, get your PhD, and then take the stuff you didn't publish and form a startup. And then almost always in our current system, when you have a startup, the goal is to get bought by one of the big corporations as quick as possible. Shark Tank style, because then you can hand it off to somebody else and go do something else or retire at 30 or whatever.
Yeah. I was curious. Good job.
It is a cool job. If you like solving the practical side of things and figuring out how to leverage what you already know, then engineering is a good field to go into for that. But medicine is basically engineering but biological systems.
Right.
For the most part. So it's pretty similar. They're both an applied science. All right. So we know how to move functional groups around. Our other category of reactions were reactions that change the carbon structure. That opens a whole nother range of possible products, right? So if you don't need to change the carbon structure, it's pretty straightforward. It can take a little bit of practice to be able to see the pathways, but it's all doable. These cleavage reactions or our addition reaction where we can add more carbons on, give us a bunch more options. So if we started with 5 carbon atoms, if we can put our alkene in the right spot, we can chop off 1 carbon at a time. And so it's moving the pi bonds around before you get here can still be really helpful. Start from a larger molecule, we'll add a bromine, move the bromine where you want, turn it into a pi bond, chop it out. Right, and then the flip side of that, if it's not a cleavage reaction, we can have an alkylation, or also called a coupling reaction. When you couple 2 things together, that means like linking them together like a seatbelt, fastening a seatbelt.
That's like the last step in the reroute.
Similar determination steps. In this case, the way that we have to link together carbons reliably right now is pretty much always going to go through that deprotonated alkyne.
Okay.
Because that turns the carbon into a nucleophile. We'll learn the end of this quarter a couple more options for adding carbons to things, but for now, this is the only reaction we have. Carbons is you turn a carbon into a nucleophile, and you get an alkyne, which then we can hydrogenate if we want to get rid of the alkyne. So making the alkyne, deprotonating it.
What the X?
It's a leaving group, so X is a halogen, right? So it could be a bromine, could be an iodine, could be a chlorine. So I already mentioned this term, retrosynthesis. Just means working backward. There are retrosynthetic arrows that specifically mean you're going backwards. So if you see arrows drawn like this in chemistry, that means you're actually thinking backward. I don't like that though, because I'd rather just write from right to left. Because this is confusing to say, I'm writing from left to right, but I'm thinking from right to left. Doesn't make a whole lot of sense to me, so I don't use those arrows. But if you see an arrow like that, that just means we're thinking backward. All right, so how can we do this one? Do we need to add or remove any carbons? No, it just looks funny because we've turned it into being linear. But that's good, because that just means all we have to worry about is moving functional groups around. How you doing? Good, how can I help you?
I like the thing. They like it.
Okay. So do you know who Caroline is?
Yes.
So I would ask Caroline, she knows
Okay.
where all this stuff is.
Cool. Something makes sense.
Yeah, no problem. Moving functional birth surrounds. So basically that limits the thing, their possibilities in a good way in this case. We don't need to get really lost.
The first thing I'm trying to do is take that.
First thing we're gonna wanna do is take the OH out.
Now that the first step is gonna be seven. Yes.
Then once we make it a good leading group, what are we trying to do? Where are we trying to go?
If we stop with the, like, at the intermediate, like, if we don't do the second step to remove the OH like we have, then it already adds a high bar. Right?
Not quite, adding this just would turn this H into a TS.
That and then to we and the
So that's just gonna give us an elimination reaction. And in this case, because our OH is already the end of the carbon chain, we don't really care about theta versus Hoffman, right? So that's gonna give us this molecule, right? How many ways do we have to make an alkyne?
too many. No, just water.
So where do we have to go to get here? If we only have one reaction that makes an alkyne,
Well, it has three numbers in the arrow. Right? So we have one is gonna be BR2. Is this slash like a problem? Because I have BR2 slash CCl4 clear.
that's a good call, yeah. So the CCl4 is just your
It's with, right? It's not,
solvent,
it's not like this word.
right?
Okay. So step one is gonna be BR2 slash CCl4.
That'd be our last step, right? Or you mean from here?
From there, right?
Yeah, because Br2 gives you a bromine on either side, right?
And that's what we just made first, right?
That's actually the second arrow. First arrow was leaving group and then elimination reactions made this.
Yes, that was.
Yes, yeah, and this is our second question mark.
So then we do the excess NaNH2.
So don't get too hung up on the number of arrows here. Or the number of question marks. Because once we do this, we just did NaNH2 once. We would just get this still with the bromine attached, right? And then it does it again. To get your final product. Because we're gonna show the intermediate. So after we added one equivalent of NaNH2, we get one elimination reaction done. And then if we add more NaNH2, we get the second elimination reaction, which gives us our final product. That was just showing the intermediate basically. If you just leave it with the excess, you don't need this intermediate. You can go straight to your final product.
Race, it was ready. The race.
So the intermediate just looks like you pulled one of the bromines off.
That's it, and then this. Yeah. Cause it just pulls the, see how from here to here, all you do is pull one of the bromines off, add the bond. Do you see that? Okay, so then you're just gonna do it again, it's what? It's. Yes.
So that's what we see. Those with fluoride and pyridine, followed by any base. They use the sterically hindered base, but it doesn't have it. Followed by Br2 in carbon tetrafluoride. So we get the dibromination, followed by excess NH2, which then we followed up with water just to make sure we didn't leave this deprotonated.
I haven't understood.
So really, we actually might get two intermediates in this last step. We get one that looks like the still with one of the bromines attached. Then we get the deprotonated alkyne, which then when we follow it up with water, we get our final product. Because basically we're gonna go past the alkyne if we actually have an excess of 5. So the water is just there to give that final step as a proton source. So this is just showing the intermediates for these. So the first thing that you do is you do the first intermediate that we drew on the last slide, right? But then technically, if you really have excess sodium amide, it's gonna make the alkyne get deprotonated. So we kind of get another intermediate. So step 2 on this last part is just add some water so that we can protonate that alkyne and not leave it as an alkali. So really, I'm just reminding you too of what this mechanism is. And the last one is 2 more practice problems. But I think we'll end there for today. We'll leave these as a warm up for next Tuesday on our review day. And then this weekend, rather than a quiz, we'll do a practice test. So it'll be due next Thursday. But I'll make it available this weekend. So if we work on it this weekend a little bit, that way you can come to Tuesday's review with an idea of what questions to ask.
I was also on that address. Are we supposed to know like how many carbon fibers have in their spectrum? Because we don't have anything saying for it. And I usually like when we up here,
No, but you know what the structure and coordinate is.
like it should look like that.
Right. Except without the double bonds.
So we have this one.
Right. So that's normal coordinate all. That's the product. You started with no OH and double bonds. So go back to your other drawing there. The no double bonds also count your bonds to that carbon. That's a CH2, not a CH3 up there.
Okay,
Otherwise, you get a carbon with 5 bonds.
all right.
But yeah, so you're gonna start with. So yeah, go through and count your formulas, but if you know the structure, you should be able to get the formula. All right. Good job this week. We're on schedule. It's not very often I have a class where I can say that at midterm. So we're doing well.
It is long.
It is.